In this video, you're going to talk about types of chromatography, specifically gas chromatography. We'll explain to you how that works, and then we'll move on to what you will be asked in the exam before we move on in the next video to the exam style questions to complete the topic. What is chromatography? Well, it's a method of separation that you may have used at GCSE using paper. Okay, but this time we're going to use gas, and we're going to have a mobile phase, which is a carrier gas, and a stationary phase, which is a high boiling point liquid or a solid on a column. But we'll explain that in a bit more detail in the next slide or so. So first of all, it is a box. A gas chromatograph is a box essentially with an oven. You can see the door to the oven at the front here. So this thing, you just open it at the bottom, and inside there will be an oven. Now, because it's an oven, it only separates thermally stable compounds, so you can't use anything in there that will break down. You can also see here, okay, and here, you have injector and detectors, okay? So you inject into the column and then it goes all the way around to the detector. But again, we're going to show you that in more detail next. So the separation consists of a stationary phase, and that stationary phase is the high boiling point liquid or solid supported in a column. And that column is coiled inside an oven that can be set to a specific temperature. And as you know from my bio, my name is Dr. Beard, and my PhD was mainly on gas chromatography. And I can tell you that these tubes are tiny. They are 0.25 millimeter across. They are absolutely tiny. And so you're forcing all your compounds through, and some of them, if they've got a big molecular mass, take longer than others. Okay? And the reason they take longer is because they're attracted to this high boiling point liquid. So here is a schematic of the column. Just imagine it's cut down here, and you can have a solid packed into the center or a high boiling point liquid. If you have a solid, it separates through adsorption. So imagine your compounds going through the middle of this column here. So it's going through there, okay, and it's attracted to the solid in it. So it's attracted a little bit, and so it slows down the larger molecules, and the smaller molecules go through a bit quicker. If it's a high boiling point liquid in the center of this column, here and here, okay, it separates through relative solubility. So your compounds, if they're polar, for example, and the boiling point liquid is polar, they dissolve a lot, and so they'll stick and they'll take longer to go through the column. If they're not soluble in this high boiling point liquid, they'll just go through the column very, very quickly. But we're not going to concentrate too much on that, because in your exam, you're going to mainly be asked about interpretation. So let's just quickly go through what the actual machine looks like. Here is your coiled column that I said was only 0.25 mils in diameter. Okay, and then you have your carrier gas, which is your mobile phase. And it's an inert gas, which means it doesn't react with your compounds that you're separating. Go through a regulator and then go to the gas flow controller, which controls the flow rate, so it keeps it constant. Then you have that going into the injector. So that means when you inject your substance with a syringe, okay, and you inject it as a solution, mostly, so therefore you calculate the micrograms per centimetre cube normally. And as that goes on to this column, it goes round and round and round inside an oven, okay, and the carrier gas pushes it round and round and round until it gets to the detector. And so the compound, you time how long it takes to get from the injector to the detector, and that's called the retention time. So how long was the compound retained by the column? Once it gets to the detector, it goes to a computer. The computer analyzes it and gives you a chromatogram. Now we're going to look inside the column. You can see we've injected 3 different samples here, the blue and the red and the yellow. The carrier gas comes in, and as the carrier gas comes in at a constant rate, it starts to push these molecules through the column. They are attracted at differently to the stationary phase, or which is a high boiling point liquid or solid, okay? And through adsorption or relative solubilities, they start moving at different speeds. Now, usually the one with the lowest molecular mass moves the quickest. Now, if that's the case and the carrier gas keeps on going at that constant rate, eventually the yellow one will come off the end and go to the detector. As it goes off to the detector, it creates a peak. Now, really important in terms of definition, the retention time is the time it takes the compound to go from the injector to the detector. So you inject the sample, you time how long it takes, and then when it gets to the detector, you take that time, and that is your retention time. As the compounds come off the column, you can find out lots of information. For example, that the peak area is relative to the amount of compound present. So let's have a look at a chromatogram. Imagine this is being run over many minutes, and each time it's gone from the injector to the detector and has a retention time of 5 here and about 14 here. You can see here that there are different areas underneath each peak, and then you can normally get a readout telling you exactly what they are, and in an exam they'll give you exact numbers to show you what they are. Okay, so you can see the relative amounts of this, but you can't know the actual amounts of this unless you do something else, which is called a calibration curve. So the calibration curve is written here. Notice at the bottom it says concentration, milligrams per centimetre cubed, and all that somebody's done is had different concentrations of A and B in this case, okay, and they've injected them and done different runs, and they found that if you inject, for example, 20 micrograms per centimetre cubed, then you will get 32, 33 or something here, peak area. And what we can do is then work that backwards. So we can go from a chromatogram here, so let's put our chromatogram back out with our peak area being relative to the amount present. And we've got our chromatogram, and from there we can get our peak areas. And we've put it in red to show that this is the red calibration curve. Okay, so you've got 23.9 here. So all we do is take that peak area, come across here, and obviously you do it more accurately, and we'll show you that in the exam style video. 23.9, go across, come down, and then you can pick off your concentration. Now, just to summarise all of this, gas chromatograms give the retention time, which can be used to identify the compound. So, for example, you can look at that retention time, inject a standard, inject on the same program, you can inject the same compound, and if they come out at the same retention time, they're the same thing. Okay, so you can use it to identify the compound. You can use it to identify the number of compounds in a mixture, because it will be the number of peaks. You can also use the concentration of each compound present, okay, by using a calibration curve. So if you have a peak area, you can use that peak area and compare it to your calibration curve, and that will give you your concentration of, for example, this compound. And remember, the higher the peak area, the higher the concentration of the compound relative to each other.